Thank you for tuning in. We are about to experience ABot AI today. Let's get started. Given any artifact from network, ABot AI is capable of performing in-depth analysis and identify specific 3GPP call sequences. Driven by augmented intelligence, ABot AI can perform deep packet inspection, use novel and classic ML algorithms to detect anomalies, and provide actionable insights guided by generative AI. ABot AI, powered by generative AI and 3GPP specifications, uses all kinds of communication data like packet capture, network logs, KPIs, and system specific configurations to analyze anomalous behavior in network. Logs and KPIs collected from several sources are used to correlate and inspect information from multiple network functions. ABot AI uses LangChain based multi LLM analyzer for error diagnosis and generates comprehensive, context aware, actionable insights. Once the network artifacts are uploaded, ABot AI will process PCAP, correlate UE, and identify 3GPP procedure per UE. Once that is completed, first ABot AI will look into its native knowledge database to collect insights for any anomalous behavior that it has observed in the PCAP. If the native knowledge database is unable to provide insights, then it proceeds to LLM framework to generate insights from PCAP. We will see examples where this stage is skipped altogether just because the native knowledge database was enough to provide the insights. Once the PCAP insights are generated, ABot AI will use correlated logs from various network functions and LangChain based multi LLM framework to generate log based insights. Once all the insights are generated, ABot AI will summarize and consolidate those insights. It will also generate a coverage statistics report and a final actionable insights summary. This is how the coverage statistics would look like. Per IMSI, it will give a detailed description of all the procedures that were executed in network. Here's the first look at the actionable summary report. However, we'll look into these in detail once we show the use cases. Now let us look at a few interesting live cases. Let's analyze this 4G case of initial attach rejection. Here, eNode B had sent an initial attach request to MME. MME, instead of accepting the request, responded back with an attach reject. We have finally consolidated the insights. Now let's go through them. First, we have an issue that was encountered once for this particular IMSI. The consolidated insights clearly indicate that there was an IE with invalid length. Let us deep dive into the errors further. This is the main issue identified from the PCAP, which says that a particular IE had invalid length. That particular IE was contained in a message that was being transported from S gateway to MME through S11 interface. The following dependent errors were also observed. First, we had an invalid length issue with some information element, which presented itself as a request rejected by serving gateway or PDN gateway when it was transported back from MME to eNode B through S1 MME interface. This framework can not only capture the root cause of the failure, but it also indicates the propagated issues that had stemmed from the original failure. Let us look at a couple of more logs for this case. If you see here, it clearly says that there was an unexpected message interrupt caused by this invalid length of an information element. This wasn't the only issue that was observed. We also saw that this particular issue was encountered twice for unknown IMSIs. The summary says that this error is typically associated with eNode B not recognizing the provided UE's S1 AP ID, which prevents it from releasing the UE context. If we deep dive into the issue, we will see that the actual inference was unknown ENB UE S1 AP ID, as mentioned in the summary, and this particular issue had occurred in a message being transported from eNode B to MME through S1 MME interface. In all, we identified 3 total issues in this artifact. 1 for this particular IMSI and 2 for unknown IMSIs. In this case, ABot UE Gnode B had sent a PDU session establishment request to the 5G core to establish a PDU session. The core rejected the PDU session establishment request and responded with a PDU session establishment reject message with proper cause. Here's the pipeline that analyzed the artifacts for the case. Notice that the PCAP insights were generated from native knowledge DB, and the PCAP LLM stage is skipped altogether. Let us look at the insights. I've highlighted the issue from the summary report. The summary report clearly indicates that the error, that is the PDU session establishment, was rejected because PDU session could not be created due to a no subscription error. This summary is further substantiated by excerpts from the artifacts. The error identified from the PCAP is described in detail here. In PDU session establishment procedure, it was rejected with a PDU session establishment reject message. The 5GSM cause IE was returned with a value 31, which means the request was rejected due to unspecified reasons. The message was propagated from AMF node to Gnode B node through N1 N2 interface. We see further support of this issue from the logs. In SMF log, we clearly see an error for PDU session creation due to no subscription error. which is propagated from AMF to Gnode B as PDU session establishment request rejected by SMF. Let's see another case. Here too, after initial registration, PDU session establishment request was sent to the core. However, this time, PDU session establishment was accepted. On further analysis, we found that PDU session was not established due to issues in the core, although the AMF node responded with an accept message. This is a particularly interesting case because although here the core says that the session was established, reality was otherwise. Let us look at the analysis report of this case. Here you see the first log indicates an issue with PDU session type IPv6 not being allowed in DNN configuration, and this is why the session could not be created. This insight is further supported by an SMF log that says PDU session IPv6 is not allowed in DNN internet configuration. Along with the logs, we also found some insights from the 3GPP procedure sequence in this case, and that is highlighted over here. In PDU session establishment procedure, we were expecting a PDU session reject message because in reality the PDU session was not established from AMF to Gnode B node. However, the core responded with a PDU session establishment accept message from AMF to Gnode B node. Here, ABot AI was capable of identifying the issue in the core, even though the core could not identify the issue and respond with the proper message. Here we have the case of PDU session establishment rejection. After a successful completion of initial registration between ABot Gnode B and a commercially deployed disaggregated 5G core, when a PDU session establishment request was sent, instead of a PDU session establishment response, the core responded with a rejection message. The summarized insights clearly indicate there is a bad SQL grammar exception, and the logs also show an error in relation to this particular element. If we deep dive further, we will find the actual issue identified in the packet captured. In the PDU session establishment procedure, we had a particular information element within a message that carried the request rejected indication due to unspecified reasons. This message was being transferred from the AMF node to Gnode B node through the N1 N2 interface. If we look further into the logs pointed out by ABot AI, we will see both SMF and AMF logs gives this bad SQL grammar nested exception indication. Since we have worked with the team responsible for maintaining this core, we can actually say that the issue hinted at here by ABot AI is in fact the actual reason for failure. Once this issue was resolved by the team, this particular case of PDU session establishment was a success. Next, we have PDU session modification rejection. After initial registration and PDU session establishment, ABot Gnode B was attempting to modify the PDU session by sending a PDU session modification request to the commercially deployed all-in-one private 5G core. However, instead of responding with a PDU session modification response, the core rejected the modification request. Here's a first glimpse of the consolidated insights. This particular issue was observed once for this MZ. The summarized insight report indicates a failure in the PDU session modification procedure, which was rejected by the network. A deep dive into the issue shows that it was indeed the PDU session modification procedure that had failed, and the cause of the failure was a network failure in a particular information element carried in a message being transported from AMF to Gnode B through the N1 N2 interface. Looking at the various logs identified by ABot AI, we see the issue indicated in the SUT log as failed to find SM context with NSMF ref 170. Let us look at another case. Here we are trying to terminate an established PDU session. For that, ABot Gnode B has sent a PDU session termination request to the all-in-one P5G core. However, the core has rejected the termination request and responded with a NAS downlink transport message. The consolidated insights indicate the issue was encountered once for this MZ, and the issue was a failure in PDU session release procedure due to message type non-existent or not implemented, which is also indicated in the detailed error report collected from the packet. The same issue is captured in the log as well. That's all, folks. Thank you for joining us today.